So, wonderful good afternoon, and welcome to the last talk of the session. So, this is me. You already heard a couple of things. Most importantly, perhaps on this slide, I'm also an organizer of the Munich C++ user group. In other words, I like communities. And this is kind of a community here, so a great way to introduce new friends, new friendships, etc. So, I want to start with this. So, let's do something you've not done before. Look at your left neighbor. And repeat after me. It is a pleasure to sit to such a motivated and talented C++ developer. That's great, doesn't it? Okay, now of course we should reply to this nice introduction. So take a look at the right neighbor and reply, yes, I like myself too. Yeah. So, in this 1 hour, we are now talking about essentially one question: what is C++? And I know there has been a talk at CPPCon 2019 entitled with "What is C++?" and actually discussed this topic in quite some depth. So this is not where I want to go. In particular, I'm interested in a variation of this question: what kind of programming language is C++ today? And I think the obvious answer comes to mind pretty quickly. Of course, it is an object-oriented programming language. And this is, for instance, something we learned from the book Code Complete. One of the best books I can recommend, but it clearly says C++ an object-oriented language. And this is a pretty common theme. So look at this website, for instance, learncpp.com, tutorials to help you master C++ and object-oriented programming. Of course, people that learn C++ immediately make the connection, this is what it is. And this is, I believe, really deeply embedded in the minds of people. So just 2 weeks ago, in the CPPcast interview of Brad Larson, I'm definitely not picking on Brad, so this just slipped his tongue. Overall, you can get up and running pretty quickly with an object-oriented programming language like C++. This is something that apparently is really deeply embedded in our minds. But luckily, there is people that kind of try to tell you differently. So, the first talk that you might have seen is Inheritance is the Base Class of Evil. A talk that I really recommend. It's just 20 minutes, actually 25 minutes. But this is a talk that takes a totally different direction. No, we don't want to use inheritance hierarchies. This is bad. This might actually break your things. Pretty surprising, pretty negative. And there's more. Last year, CPPCon, there was a talk about object-oriented programming. But this talk does not start as you would expect it. The talk starts like, well, nobody would expect this talk at CPPCon because the cool kids don't use object-oriented programming anymore. I just do this because there's so much legacy code out there and they need help. Really negative. And there's people that even go beyond this. OOP is dead. Long live data-oriented design. Okay, this is definitely too negative, but apparently there is a pretty negative attitude towards OO in the C++ community. Perhaps you should talk about this also. However, there's also other talks, like this guy here. This was probably one of the first talks that took a different route. Jean Perrin talks about algorithms, and essentially the one guideline he gives you is no raw loops. This is the essential slide from the entire talk. If you've not seen it, this is a must-view. And there has been a couple of successing talks like Jonathan Bocara's 105 STL algorithms in less than an hour, which is also a talk that I definitely recommend. And recently, last CPPCon, Connor Hoekstra with algorithm intuition. A lot of talks about go in the direction of functional programming. And this is obvious, most obvious here in this talk, functional C++. Totally different direction. And if functional C++ is not enough, then there is also, of course, functional C++ for fun and profit. So, there's a lot of people that are arguing in different directions. And this is exactly what I'd like to talk about. What is C++ really? Let's take a look at Wikipedia, because Wikipedia should know. And on the right, there's a summary. What is it? Multi-paradigm. Procedural, functional, object-oriented, generic. It's kind of everything, which is unfortunately also not a particularly satisfying answer. So, what I want to do is I want to look at designs. I want to look at common solutions. I want to try to give some answer to this question. Is it procedural? Is it object-oriented? functional, generic, or just all of it? All right, so let's see. Disclaimer first. Of course, C++ is pretty complex. I do not think that I can give a complete answer. It's an attempt to give some point of view, and probably you have to go from there in various other directions. Then, of course, C++ is giving you a vast solution space. I'm going to a portion of it only. I only consider solutions that use dynamic polymorphism. If you can use static polymorphism, perfect. Then you have even more solutions. I just restrict myself, also for the sake of time, of course. Then I only consider the state of the art of C++. Actually, we are already a little bit ahead of this, but this is probably not something that you could use right now in production code. So I only consider C++ 17 and whenever necessary also 20. And there will be a lot of code. There will be indeed, there is a lot of slides. However, it's not about the details. I try to point you to the very important things that are relevant to the according designs. It's about the general image, the general picture. So it's about the design. And I deliberately choose a very simple problem. It should not be about the problem. You should not think about the problem too long. And so I chose what you see in the beginner's course also. I want to draw shapes. And for the sake of simplicity, there's also only two different kinds of shapes. There's circles and there's squares. All right. The first possible solution to this particular problem is a procedural approach. So I start with an enumeration that tells me clearly, oh, all right, there is a circle and there is a square. And there's a base class 2, which I call shape, kind of the abstraction of that. And shapes, first and foremost, are base classes. Well, it has a virtual destructor. But in this special case, the shape takes one of these enumerators. I remember what I am. So I remember as a data member whether I'm a circle or a square. Now, the circle class inherits from this shape. And so it has to initialize the base class. Well, a circle is a circle, of course, so it initializes its base class with the circle enumerator. Of course, then there is all kinds of circle-like stuff. There's a radius. There is definitely a couple of member functions that you can use to query the things. There's a radius, center point, rotation, whatever. And there's operations on a circle. Everything I need, I can get from the public interface. So there's no point in putting them inside the class. So translate, rotate, and my draw are free functions. As I said, it's just about the design. We focus on 3 operations. That's perfectly enough. Then, just for having 2, there's a square 2. A square, of course, initializes its base class with the square enumerator. Yeah, I'm a square. I remember that I am a square. Else, it is absolutely equivalent to what you've seen before. All right. Then I want to do something with this. I said we are drawing shapes. And so let's assume that we have one function that gets a quite bunch of shapes. A whole bunch, a vector of shapes, probably managed by a unique pointer. And what do I do in order to draw a lot of shapes? Well, I traverse this vector. And I have to ask nicely, what are you? Are you a circle? Well, in case you're a circle, then I draw a circle. Of course, I have to cast accordingly because it's just a shape pointer, but I draw. And in case it's a square, then of course I do the equivalent thing for square. All right. Now in the main function, I first of all make my life a little simpler. I create a type alias, so vector of shape pointers is now just called shapes. And I create one of these vectors and I add a couple of shapes. A circle, a square, yet another circle, and I draw them. And surprisingly, of course, 3 shapes are drawn. Nice. So, this is the first solution, which works. However, I do not believe that you're particularly happy at this point. So let's rate this and let's see why you might not be particularly happy. So I have 5 categories for rating solutions. The first category is the addition of shapes. I want to add new kinds of shapes. Now, of course, there's more than 2. Then I want also to add new operations. I can translate, rotate, draw, but there may be more. Then I'm interested in the separation of concerns. how entangled is the logic with state. So I want to separate things as much as possible. Now these three mention design principles, OCP and SRP. Do you know them? So I just for the sake of repetition, let's practice these. Let's mention all these solid principles. It's important anyway. So the first one is the single responsibility principle. Then the second one is the open-close principle. Then we have okay, now you're getting warm. Great. The I is the principle. Then and the D, last but not least, the dependency inversion principle. So we will only need the first two primarily. I will point out the others in some small cases. However, this is the first three categories. Then I'm interested in the ease of use. How easy is it to use the according design solution? And of course, obviously, performance. So the enum solution. How easy is it to add shapes? Well, if you think about this, this is probably the worst thing that you can think of. This is the worst thing. So one means very, very bad. This is a maintenance nightmare, essentially. You have to update a lot of places in your code. This is exactly what OCP tries to warn you about. You have to go to a lot of places and you have to find all these places. It is very, very hard to find all these places and you have no guarantee that it indeed found all the places. Very hard to extend in this regard. However, adding new operations, not so bad. This is actually something I rate with a 7. So it's pretty positive. It is not particularly convenient to repeat this if, the switch statement again and again and again, but still it works. You do not have to touch other code. This works relatively well. Separation of concerns, the logic of drawing something is not deeply embedded. It's something that is extra, and so I rate this kind of, well, somewhere in the middle, 5. You will see there is much better ways to separate concerns. Then ease of use, how easy it is to use the solution. Well, from a feeling, I would say, so somewhere in between. Yeah, again, I have to forward you to the next solution. There is much, much easier solutions. Performance. Oh, performance is interesting. I show you a couple of benchmarks. Ooh, benchmarks. Benchmarks are tricky. Benchmarks are usually, so in a room like this, there's at least 2, 3, 5 persons that complain about the benchmarks. So let's just make sure that we all are in the same page here. What do we actually compare? So first of all, I use this laptop to run the benchmarks. This is the data. I use C++ 17, 03, and the ndebug. Nothing special. I'm not really interested in particular performance values, characteristics, etc. I'm creating 100 random shapes. Just perhaps 49 circles, 51 squares, I don't care. I just make sure that in every benchmark I do exactly the same, but the compiler cannot tell. I do 2.5 million updates on each one. And of course, updates. Well, I'm not interested in measuring drawing. This is really not interesting. I'm interested in benchmarking what is the overhead that a particular solution gives me. So I try to make the drawing really, really cheap. The operation itself is there's almost nothing. It's a cheap vector addition, usually one AVX instruction. The compiler cannot optimize this away, though, and so I should end up with the overhead of the solution itself. And then I normalize it to this particular solution. So in this case, the performance is just 1. So this is my baseline. And I can tell you right now, you see it from the scale of this graph, this is going to be a pretty fast solution. And although you don't like the solution at this point, you might realize that there is actually a big virtue here. Performance. This is why the solution is used quite a lot in computer games, for instance. Performance a full 9. You will not see a lot that actually outperforms this. However, still, despite the fact that it's fast, you don't like it. You would reach for another solution. I believe I know exactly which keyword popped up in your mind when you saw this solution. I believe you immediately thought about virtual. This is what we have virtual functions for. So, second possible solution, I'm now using virtual functions. The enum is gone, there is no enumeration anymore. Instead, my shape-based class just mentions all the operations that I have. So there is translate, there's rotate, there is draw. So, of course, this is again our 3 example functions. Then the circle does not have to deal with any initialization of the base class anymore. Doesn't need to store anything, but now it of course needs to implement these 3 virtual functions, whatever it takes. All right, not a big secret here. The square does exactly the same thing, implements these three functions. Some of them might be similar to whatever a circle does, but drawing is definitely different. Now, how do I draw a whole bunch of shapes? Well, this suddenly turns out to be pretty simple. Oh, this is beautiful. This is now the open-close principle in action. I don't need to know about the shape type anymore. We just draw the thing and be done with it. In the main function, nothing has changed. It's still the same setup. I create a couple of shapes, put them into the vector, and I just draw all of them. All right, is this better? Now, let's see. So, the OO solution, additional shapes. Oh, actually, when you think about this, you realize, oh, this is now harder. No, sorry, this is now better, but adding operations, sorry, this is much harder. So, adding shapes works pretty well, but adding operations would require me to add new functions into the shape. Can you simply add from somewhere a new virtual function into base class? You cannot. And suddenly, you realize this is not the same solution. It's an inversion of the solution. It's a different solution, different properties. We cannot really compare them anymore, at least not in these things. Of course, well, I want to compare them somehow. Separation of concerns. Well, now I have a draw function inside the class. All the implementation details go inside the class. Now, if you decide on OpenGL and then later decide to use something else, you have to change the circle class, which does not sound proper, which sounds bad. So this is going down. The implementation details are now coupled to the geometric entity. Ease of use, well, I don't see a lot of difference here. So I give it the same value. From the main function, it's the same, and you will just have slightly different problems on the left side. Performance. How much did it cost us to go to virtual functions? If you benchmark this, you realize, okay, there is a cost associated with virtual functions. In my measurement, it's approximately 30% on GCC, perhaps a little more, or sorry, depends how you see it, perhaps a little less or more on Clang. 30% overhead. Well, okay, perhaps this is not particularly expensive from your point of view, but there is fields like high-performance computing or also high-frequency trading that say, no, we cannot accept this overhead. This is already too much. So 40% is out of the question. Okay, so again, this explains why solution 1 actually is a thing. Now, I rate this down to 6. We've suffered a little, but you will see actually it can get much worse. I would like to have a real comparable solution to the enum solution. I would like to be able to very quickly add operations, but of course I do not want to suffer in the other things. There is a design pattern for that, a classical one. And I believe you are just thinking about this again, perhaps a little with dread. People that use it sometimes have bad experiences, but still I'm going to show it. The visitor design pattern. So this is one of the famous gang of 4 design patterns, one of these 23. I have no idea if you all are aware of or know this in detail, so let me explain this in just one slide. On the right-hand side, so this is directly copied from the gang of 4 book. On the right-hand side, we have an element hierarchy. For our purposes now, this is the shape hierarchy. So I give it the names that we are now familiar with. I have a shape base class, and there's circle and there's square, potentially other shapes as well. Now there's one very, very important assumption about visitor. We assume that the right-hand side hierarchy is a closed set. We assume that there's not going to be any other kind of shape. We know that we know all of them. However, what we do not yet have is all possible operations. So perhaps we can think of a resize or a reshape, whatever. We don't know all the operations. And we would not like to change the entire right-hand side hierarchy whenever we add a new operation. This would mean that I have to add a virtual function up here and implement in every possible derived class. A lot of changes on the right-hand side. I would like to avoid that. And this is where this left-hand side hierarchy comes in, the visitor hierarchy. A visitor is essentially an abstraction of some kind of operation. The base class is traditionally called visitor, and it has a visit function for all the possible shapes, for circle, for square, whatever you have. And this is again where this assumption that we had before hits us. We know about all possible shapes. When we have to add a new kind of shape, we have to change the left-hand side hierarchy. Now, I said this is operations, so perhaps the visitor is now implemented by means of rotate and draw. Two example operations, and all of these operations now implement a visit function. The visit for circle and a visit for square. On the right-hand side, I now just add one more function, the accept function. This is also a traditional name. The accept function accepts a visitor and is implemented by just forwarding the request to the according visit function. So please visit me, apply this operation to myself. And so ultimately it's a double dispatch scheme. You call accept calls visit, the second virtual function, and then the operation is run on your particular shape. So there's a couple of good things about this. If you now add a new operation on the left-hand side, you really don't have to touch anything anymore. You just add code. This is perfect from this open-close point of view. However, it does not work well if you add new shapes. Then you have to change the entire left-hand side hierarchy. So let's take a look at code. How does this look like? We start with a visitor. I use the same name. This is just reasonable. I have a visit function for both circle and square. Then a shape base class. Now much smaller, easier, and there's only one virtual function called accept. It accepts a visitor. This is the function that now needs to be implemented in both circle and square. All right. Then the circle class is to some extent just a regular circle with the exception of this accept function. Accepts now implements the necessary steps for dealing with a visitor. It just calls the according visit function, passes the this pointer, please do the thing you have to do on me. Else it's pretty much unchanged from the thing we've seen before. And also square, no changes here except for the accept function. It's exactly the same implementation. It really is identical code, but the this pointer is of course different. So you cannot omit this or move it to a base class. Now let's implement an operation, draw. And this is now where this visitor is really strong. I do not have to touch anything. I can simply say I need a draw operation. I can work on the public interface. I implement visitor. I override all the necessary visit functions, and I'm done. Perfectly independent from everything else. Drawing a bunch of shapes now changes slightly because there is no draw member function anymore, but there is actually an accept function, which I just pass the operation. Note that I explicitly create a new object for every call. This is not necessary, of course, but actually this is faster. You will see that this actually proves to be pretty clever. It could be worse. In the main function, again, nothing changes. I still create a bunch of shapes, put them in a vector, call draw, and run benchmarks. So, how does the solution compare to the solutions we've seen so far? First of all, adding shapes is again pretty difficult. Pretty difficult because I have to touch a lot of code. I rate it up a little bit in comparison to the Unum solution because at least we have the compiler to support us in a better way. It is still a very, very unpleasant experience, but the guarantee to really fix everything is better than in the first solution. Adding operations, pretty good. Very, very low coupling here. This actually works splendidly. This is what a visitor is supposed to do. Now, because the operation is outside and because it's totally independent of the shapes itself, so I don't have to change shapes to add an operation, actually this is pretty good as well. Much, much better than in the first solution, which I write it down primarily because I always have to know about all the shapes in every function. This is nicer, much, much nicer. Ease of use, though. Oh, if you've talked to somebody who uses visitors excessively, they will tell you it is a nightmare too. Yes, of course, it is supposed to work fine, but it is actually pretty complex to understand and to get right. So from a usage point of view, I have to write this down. Visitor is not particularly pleasant. And also you have to deal with two inheritance hierarchies. But there's something worse, the performance. So in comparison to the other solutions we've seen so far, oh my, we are paying a serious overhead. And I said before explicitly that I'm not doing something expensive in the operation. This is just the double dispatch that we see, two virtual functions. A very cheap operation inside, so there's a lot of overhead due to this design pattern. Okay, GCC gets it better than Clang, but this is not the point. It is much, much more expensive. So unfortunately, I have to write down performance to 1. That's probably not getting worse than that, at least not in this presentation. However, we are not talking about modern C++. And modern C++ has the according solution for this particular problem. And I believe that at least 50% of you are now thinking about a feature that has been introduced in C++ 17. Stood variant. So, in C++ 17, we would rewrite this entire thing and use a variant instead. So, first of all, I'm back to the circle. Note, there is no base class. There's no base class at all. We don't need a base class anymore. I implement a circle. It is nothing as simple as this circle because there is no virtual function, there is no indirections. It's a straightforward circle. This is something that you can show in a beginner course on perhaps day 3 or 4. Easy. Then square. Also no surprises here. As simple as it gets, it is just a properly encapsulated square. Now, for a variant, I need operations too. These operations are now nicely extracted. I can implement some function object that provides me with call operator for circle and square. So, draw is totally independent of the circles, except, of course, they need the public interface. A variant is now either a circle or a square. So this is the C++ 17 feature I mentioned. It's like a union. So if you've not heard about it before, think about this as a glorified union, but much better, type-safe union. However, if you see that, something that can be either a circle or a square, what is that, conceptually? Well, if you would have to give it a name, we would choose shape. Well, this is a shape. That may be the reason why we don't need any base class anymore. We have some kind of abstraction here also. Also, we don't have to put pointers to shapes anymore into vector. We have now a vector of these variant objects. So I now get a vector of shape. I draw them. And in order to apply an operation, there is a function that terribly reminds you about the pattern I mentioned before, the visit function. Yeah, this sounds like a visitor. Please apply the draw operation to the according shape. Do this for all the shapes, be done with it. It looks nicer, most certainly. Much more straightforward. And it's becoming really, really beautiful if you take a look at the main function. So what do? I create a vector of shape. I call this shapes again. No pointers. And fascinatingly, I just create circles and squares and put them in a vector. Something that we cannot do before because, well, we needed an abstraction, we needed these pointers. Now I actually don't really care. Everything that it could be, everything that a variant takes, I can simply add to the vector. Really, really nice, really beautiful. Also something they can show to a beginner. The beginner will understand. All right, now, stood variant is, if you talk about adding operations, well, adding operations is again, adding shapes, addition of shapes. Well, this is where it also is very difficult to do things. If you add something to the variant, all the operations need to adapt. Same problem here. But I like it a little better again. So, okay, a slight nudge. Let's make it a 3. It's still in the right numbers. It's not good. But adding operations, oh, seriously beautiful. Really simple. You barely don't have to think. This is a full 9 from my point of view. Separation of concerns. How well are the operations detangled from the actual state? So, meaning the shapes? Perfectly. There is no connection anymore. This is also a perfect 9 from my point of view. And what do you think? Is this easy to use? Is this nice to use? Is this something that you can show to your colleagues and they say, hey, I get it? Well, I hope so. I certainly hope so. I don't know colleagues, but I would rate it with a 9. Performance. Oh, this is where I would like to tell you performance is amazing. Unfortunately, in the benchmarks, STUD variant does not show up as good as I would have expected. So there is approximately an overhead of 75–80% in comparison to the enum solution. Oh, this is a bummer. I was a little disappointed, I have to admit. I expected more, especially because all everything is actually perfect for getting maximum performance. However, I did not falter. I looked a little bit to other libraries and I've, okay, first an explanation, sorry. What is the overhead that we get here? Well, standard variant promises you to have constant time dispatch on the operations. Constant time dispatch on an arbitrary number of elements is, well, easy to do if you use function pointers. So there is a const expert array, which I call table, which is filled by function pointers that are eventually used to dispatch. And these function pointers are simply filled by lambdas. So you don't have to understand this entire code. This is what the slides are for. You get this later. But, well, there is function pointers involved here. And this is not perfect. However, I kept looking, and there's another implementation of a STUD variant, which you'll find at GitHub if you Google for mpark variant. Michael Park has done a test implementation, an implementation that is also working, by the way, for C++ 11 and 14. So you're not forced to do C or use C++ 17. If I put this in the benchmark, ooh, this is amazing. The performance is suddenly even better than the good old enum solution. Much better, amazingly better, especially now for the first time especially in Clang. This is really surprising. So why is that? Well, first of all, he does not use pointers, but a switch statement. A switch statement for up to 32 elements, which means you cannot use 100 elements in here. So 100 types. There's a limit, an upper limit, but this actually proves to be faster, obviously. And so, okay, I cheat a little. I just want this to be nice. I make this a 9 also. Yeah, this is really good, but only if you indeed use the mpark variant version. I kind of doubt that you ever need more than 32 kind of types, but perhaps you do. I don't know. So, for a second, go back to the initial question. What kind of programming language is C++? If you take a look at this modern solution, this variant solution, how would you rate it? What kind of solution is it? Is it an object-oriented solution? Or perhaps is it a functional solution? Well, if you ask experts, like, for instance, Mateusz Pusch, he talked about this and he said, well, the variant solution is functional programming in contrast to the OO approach. And it works better. I don't think it's that simple. I think there's more to it. There's a little bit of OO programming. There's a little bit of functional programming. You saw the switch. This is the procedural approach. And of course, it's a template. So there's generic programming also. So, well, I don't want to now jump ahead, but there is a couple of characteristics that this solution has. And this is probably the important things, the important takeaways. There's not a single pointer in the solution. Not a single one. I have no interactions by pointers. No single virtual function. I still can have dynamic dispatch, but without any virtual function. No manual allocations. The only allocation that happens is inside STUD vector. And once this is allocated, there's no more allocations. It is very, very cache efficient. My object lie in this vector as objects, not as pointers. Everything is in one big array. And this is a perfect setting for a compiler. This is why it, if done correctly, runs so fast. It uses values only, which is easy to understand, easy to reason about. It follows this SRP and OCP pretty well, so at least from the operation point of view. And it promotes loose coupling. I believe this solution is just simple. It really is simple. It is much simpler than coping with all the complexity that the other solutions that we saw gave us. And this is a new theme in C++. We are trying to make the language simpler. So this is the keynote presentation from Herb Sutter from last CPBCon, where he says, well, isn't this perhaps what we really want to have? Simpler things, simpler solutions, a simpler life. And so I also agree with Jason Turner, great C++ is trivial. Okay, I agree, he had something slightly different in mind here, but it's about making things simpler. This is not a bad thing, on the contrary. This is indeed a very, very valuable property. All right, going back to solutions, I have a couple of more. We also saw the OO solution, and I rated down the OO solution because separation of concerns was not particularly great. Now, there is another design pattern that now allows us to separate concerns for this traditional OO solution. Also a design pattern that you probably now think about, the strategy design pattern. It's one of the simplest, it's one of the basic design patterns. The idea is as following. Some context, which I can give a name, in our shape, we want to at runtime configure behavior. For instance, for drawing. Draw should not be part of shape. Draw should be extracted. The draw logic should perhaps even be configurable. This is where the strategy comes in. On the right-hand side, I now introduce a draw strategy, a draw function, and now I can have different kinds of implementations. So a test implementation, an OpenGL implementation, a VTK, a Metal Vulkan, whatever you can think of, independent of each other, but of course abstracted by means of this interface. All right, this is something we apply to our solution. I go back to the OO solution and update accordingly. The first thing you see is this strategy base class. Strategy can draw circles and squares. Nice, and it's of course, again, a base class. So, virtual destructor. Then the shape base class, well, shapes still know about the operations, they just don't implement them on their own anymore. So I can translate, rotate, and draw shapes. All right, this circle class is now updated a little bit. I don't have to change a lot, I just add one more thing. I add a new data member. I now have a draw strategy, meaning I know how to draw myself. This draw strategy is provided by means of the constructor. You may consider setters as well, but let's say I just need it here in a constructor. So I'm past the unique pointer to draw strategy, I move it into my data member, and now whenever draw is called, I simply use my draw strategy. So this is how I draw myself. All right, then the square class is updated accordingly. No big secrets here. It gets a unique pointer to a draw strategy, which it moves into the data member, and essentially does the same thing here. Again, it's at this point that it's important. I cannot refactor this. The draw function is the same one we saw before. It is the function where I simply draw all the shapes. So I call draw, that's it. And now I'm in a position to implement drawing as I seem fit. So why not use OpenGL? An OpenGL strategy. It is a draw strategy. It implements all these draw functions pretty nicely. So now we can draw by means of OpenGL. In the main function now, I use this. I create a circle by passing both the radius and the according strategy. So this is how you should draw yourself. I now pass a strategy to every possible shape. Okay, I know it looks a little like overhead, but keep with me, we are not done yet. So every of these shapes gets a strategy, and I can draw the shapes as before. Now this looks like a reasonable solution, but we have actually introduced a design bug. Nobody complained openly, because probably nobody dared to complain openly. We take a look at the base class again. And we consider adding a new kind of shape. Let's say a rectangle, whatever, some other kind of shape. What happens if we now extend this base class? Well, then everything is affected, even the circle and the square, because this here is now not better than the enum I had before. That is interesting. This is something I actually see a lot because people don't really see this as easily as enums anymore. Same kind of dependencies here. So there is another of these principles, the interface segregation principle, which says no, the things that do not belong together should be separated. So I have to, in order to do this right, make this two base classes. I draw a circle strategy and I draw a square strategy. But by doing this, it actually works nicer. Now the circle, of course, gets a draw circle strategy and stores it. And non-surprisingly, the square gets the draw square strategy, stores it. So quite straightforward. Nothing changes in draw, but I now implement two different kinds of OpenGL strategy. OpenGL circle strategy, OpenGL square strategy, and so on. And of course, also pass the according strategy to the according shapes. All right, so let's rate this in a fixed version. How does this work? Additional shapes. Well, how easily can I add new shapes? Actually, they're pretty independent, so it's actually good, but I think it's a little more complex now because you always have to, in addition, create a new kind of strategy. It's more work, which makes it less pleasurable. Operations, adding operations is not particularly great again. So it's the same as with the OO solution, same rating because it's actually the same problem. But now I've at least separated concerns very nicely. This works much better, so I give it a 7. I don't particularly like the fact that still I have the draw function inside the class. There's still a coupling of operations, but the implementation details are at least gone, and I can add runtime, configure them as I want to. Ease of use, well, not too bad, but also not too good. Well, I feel this was actually simpler to use, so I rate this down a little, but still it's in the yellow numbers, so somewhere in the middle. Performance. Well, you might have realized that again we have two virtual functions. The first virtual function is the virtual function like draw, and then a second virtual function in a strategy. So we cannot expect performance to be particularly good. And we see, yes, actually it is also pretty expensive. Perhaps a little cheaper than this visitor, but it's expensive. So even if you like the solution, I don't know if you do. From performance point of view, it is, for me, just a 2. Now, this is the old way of doing things. C++11 has a better way. And I already gave you a hint. A C++11 feature makes this much more pleasurable, much easier to work with. So now, almost all of you think about std function. So what I can do to extract a virtual function is to use one of these std function objects. Std function for, well, something. This is now, for instance, what I consider as draw strategy, draw circle strategy. So I give this names to make it a little more friendly in the eyes when we see the rest of the code. So remember that now these strategies are function objects. Objects that really deal with as objects. In the base class, nothing changes. This is the same as before. I have all these operations. But in Circle, I now use function objects. Instead of being passed a unique pointer to something, I now get a function object. I probably move it in place, and I store it as an object. First of all, there's no lifetime issue anymore. It's much more simple to reason about this, because this is a copy of whatever I got. This will work for my purposes as long as I live. Then translate, rotate, and draw are unchanged. They simply forward to the according strategy. So draw, if I call this, would simply call the function object. Please draw myself. Square is the same, but it gets the according square strategy. Not a big surprise. So I just have 2 of them. All right. Then drawing. The draw function doesn't change. The strategy strategies are now implemented by means of function objects again. No base class required. I just implement class OpenGL circle strategy with the according function. The same is something I do for square, and now I can draw them both. And in the main function, I do not create pointers to something anymore. We are make unique. No, I just pass an object. So here, this is how you should draw yourself. This is how you draw yourself, etc. So it's a little nicer. However, it's not nice enough, I believe. And in order to really appreciate the beauty of this approach, I now make a couple of refactorings. The first thing that I can now do is, I don't like the fact, for instance, that a circle gets a circle strategy. Perhaps there's something else we can do. Let's go here. Let's perhaps just provide a draw function for both circle and square. A free function. Nicely separated again, completely free of any class context. Then I provide a helper, like a stand-in, a draw object that has a templated call operator that does nothing but call draw on whatever it is given. So, draw, do draw, whatever. This is now what I can use in my main function. It immediately looks much nicer. So, if I now have the draw function, this is perfectly enough. But of course, you still have the flexibility to provide whatever kind of strategy you are interested in. But we can even go one step further, because it's so loosely coupled, because there is no less things that know each other. So, what about we do that? I now take this draw object, cut it, and put it at the top of my program. I can do that because, well, it's a template that works on any kind of thing. It's a dependent name at this point, so it does not need a draw function until now. So it only will need it when we really use it. Now I can use this draw as some kind of default. So draw circle strategy gets draw object. Ooh, this sounds interesting. This looks interesting. It looks like we have now just made an implementation a default. But no, this is actually not an implementation. This is an interface. I have now created a default interface, and this is something entirely different. I do not bind to OpenGL or VTK, whatever. I just bind to some convenient function. Of course, I do the same for Square, not a big surprise. And now, okay, this here works. It's like a break. Consider it a break. This is just to raise tension, you know, so excitement. Yeah, try it again. Okay, so back online. These breaks work wonders, right? So now I have your attention again. Great. So I use this default, and now in the main function I actually don't have to pass anything anymore. It just looks like the OO solution before, but with all the advantages that a strategy design pattern really gives me. Great. So I rate the solution. First of all, it is giving the same advantages as the strategy. I now have the ability to easily add new kinds of shapes. Yeah, very, very nicely. It is again difficult to add operations, so okay, perhaps a little easier. I like it better, so my personal favorite, my personal rating is a little up. But again, I have a very nice separation of concerns, and now also a much nicer ease of use. I like the solution a lot better. It's much easier to understand, you wrap your mind around it, and due to this decoupling, I have a lot of options. Performance? Well, actually not too bad. Std function is, at least in the Clang implementation, pretty quick. I have no idea where the big difference between GCC and Clang is, but at least the Clang version of std function seems to work pretty well. So I focus on the Clang implementation. Apparently they do something better. And so it is not much worse than what we have in the OO solution. And, well, of course, it's better than the original strategy. That was the main point. And so it gets a slightly better note here, a 5. So it's not as expensive as this one, but it's not quite as good as this one. All right. Now, this is nice solutions again, the function approach. But of course, you're now thinking, well, do you have to use a function object for every possible operation? That is nonsense. So a draw strategy and a translate strategy, whatever. No. However, you can, of course, use the general idea that this function object gives you and perhaps come up with a even better solution. And I'm talking about a technique that has been introduced in this talk. No, not introduced, but probably it was one of the first times he taught it in the talk, Inheritance-Based Class of Evil. Now, I'm going to show you a type erase solution, which is a challenge. It's not totally simple, but I believe understanding the general context, the general idea is totally enough. So we start with a circle class, which is again as simple as it gets. There is nothing in this class that makes it difficult. There's no virtual functions, nothing. And operations are just extracted. Translate, rotate, and draw are just free functions that accommodate circle. Then, for square, it's exactly the same. It's as simple as it gets, and it has free functions to accommodate it. Now, shape is no longer a base class. Shape is now some kind of container. Shape takes everything that is shape-like. And shape-like, in my context, means everything that I can translate, rotate, and draw. This is a shape. Now, the first thing I do in this class, which is not a base class, so no virtual destructor, is I implement in the private part a class called model. So, my name. Model is actually a class template that gets a T. So here is a T. I have no idea what T is. Could be a circle, could be a square, but it could be something else entirely. And I store the T as a data member by value. So it's a real thing that I really own. Then, in addition, it provides operations. I rename them slightly to not cause confusion. So do translate, do rotate, do draw. This is the operations that I actually really need. This is the things that I would like to do on my object. However, this is something that I cannot store. If you don't know the type T, then you cannot make this a data member. T is something that I don't know yet. So I need something in addition to this model function. I need an abstraction based on inheritance. And this is where another function, another class comes into play. I call this concept. Again, it's in a private part. And this here now provides me with all the operations that I need. It is kind of exactly the same interface as shape before. That's the same operations, but it's in the private part of shape. Nobody knows about it except the author of shape. It is pure virtual functions at this point, and this is the function that are implemented in model. So do translate is implementing this virtual function. It just forwards the request to the free function on the according object. Now, this is what I use to store it. I now own a unique pointer of a concept. And this is why this technique is called type erasure. The type is gone. I don't see it anymore. The T is ultimately gone. Then I have a couple of friend functions. This is the function that you can use on a shape. I can translate, rotate, and draw shapes. These functions are friends because they actually use my private implementation. They call these virtual functions. This is where I really trigger the according behavior. So this goes into the concept, calls the virtual function the model, and this calls the according function on the given type, the actual type. The public interface is pretty simple. So in this simple implementation, it's definitely not complete. But as I said, it's about the idea. I now have a constructor that takes everything, and creates a model. Creates a model for T. This is stored in the pimple, and, well, then the type is gone. And of course, there's the according operations that make it copyable, movable, etc. So everything else you need is there. Of course, also the, whatever other things you might need. The operations, this were the operations in the friend section. Okay, drawing things, very natural. I draw shapes. This draw function now calls the friend function, the befriended function, which calls the virtual function on the concept, which calls the free function on the according shape, circle, square, whatever. So I kind of, via a couple of functions, go to the right thing. And because this is kind of a container that takes everything again, my main function is really, really beautiful. I have, again, a vector of shapes, anything. This even can take things that I don't know yet. I never have to update this here. So I push back a couple of things, circle, square, circle. And again, no need to create any kind of pointers, no need to specifically say what it's supposed to convert to. I can put everything that applies into this vector of shapes. And then I draw the shapes. And this does the right thing. So this is a solution that is now kind of a generalization of stud function. Stud function is one virtual function to some extent. Type erasure is now the technique behind stud function. Adding shapes is actually working pretty well again. It's the simplest thing you can do. I give it a 9 because now I can even add shapes that I didn't write. Third-party shapes. At least if I have the according operations, then it already works. And I can add the operations because it is free functions. I don't have to change any kind of code. I can make it work. Addition of operations, again, I like it a little better, so I give it a 4. It's not good, it's hard again, but at least I have to do it in one place and in one place only, in the private part of the shape class. Separation of concerns, pretty good. I rate this up also a little bit, and I feel it is also very, very simple to use. Now, you've seen the implementation, you get the idea, this is expensive, but actually it turns out to be pretty efficient. So this is now comparable to the initial OO solution, at least on my machine. So if I would rate these two solutions in terms of performance, then I would say they are almost identical, almost, yes, very, very similar at least. So I give it the same number. It's not perfect, it's not really running very fast, but it's pretty convenient. So we have now quite a number of different solutions, pros and cons. But the most important part was to answer the question, what has C++ become? What kind of language is it? And for that purpose, I now take the modern versions that I showed you, and I compare them. The first thing that is apparent is that from a usage point of view, it's really beautiful. All green numbers. Some are perhaps better than others, but of course they have other advantages and disadvantages. Also SRP, due to this decoupling ideas, works pretty well. So this is really good solutions. Then, depending on what kind of solution you're looking for, adding operations easily or adding shapes easily, well, you have the according solution. Yeah, all of these, there's something that works pretty well. So also here we're in the green numbers. The only thing that is not perfect is performance, but in comparison to the good old solutions, they're not worse. On the contrary, they're actually usually better. And so also here we get a benefit, a return of investment. So, going back to the initial question, what kind of programming language is C++? It's a difficult question. And I thought a long time about this one slide. Not an hour. I mean really days, weeks, month. What is it really? Procedural, object-oriented, functional, generic? I don't think it's any one of those in particular. I think it uses a little bit of all these. So I rule out these 4. And the only thing that is now on the slide is multi-paradigm programming. And it sounds like a reasonable approach. We use all the paradigms. All of the paradigms because all of them have some certain advantages that I would like to use. But do we really use all of the paradigms? Did you really think about these paradigms when you implemented the solutions? Are we really still thinking about OO and functional? Or do we just pick ideas? So I have to admit, I also would like to rule out this one. I would like to make a suggestion. I believe what we've just done is, and what we do when we write modern C++, is actually we don't follow any paradigm. It's like no paradigm programming. We just pick the best ideas of all the worlds. We pick the things that work best for our problem. We do not necessarily think about paradigm programming anymore. Well, I believe a couple of people here now think, okay, this is not news. This is not something that I have not heard before. Okay, std function C++ 11 and std variant is in C++ 17, so this is also at least 3 years old, if not older, if you count the boost variant. However, then I believe you have a mission, a very important vision from my personal point of view. So, this was the keynote presentation of Björn Strustrup at CPPCon 2019. The interesting number that I want to point out is this one here, 112,000 views. Oh, this sounds like a lot. And actually, I did not find any other presentation that has a lot more. So this is pretty good. Officially, however, we have between 5 and 6 million C++ programmers worldwide. That's the last number I heard in a presentation by John Culp. I don't know the number, but I assume it's much bigger than 100,000. Which means only 2% of C++ developers actually get these news. Actually, only 2% of C++ developers are aware of modern C++. And this to some extent explains these legacy codes. So, you have a mission. You are now supposed to carry this information out in the world and spread the news, which is not news, I know, but still, spread this information. So tell the people that you know, tell your colleagues that did not want to come here, tell the people that you know, even your wives, friends, etc. First, modern C++ is a thing. It's not about features, it's about a new kind of thinking. Reduce the use of pointers inheritance hierarchies, for instance. Indeed, this is something we try to achieve. Use values much more often, value semantics, and keep your code simple. We have the tools in place now that enable you to do so. Then learn about the different paradigms, but primarily learn about the advantages, the weaknesses. What do I gain from functional programming? There's actually a lot. If you've not tried it before, try it. And of course, object-oriented programming is great if you use the advantages of it. So pick the good ideas, combine them, create new ideas. And yes, there is no fits-all solution. It depends on what you want to achieve. This is the one carry-away message. If you only can remember one thing, this is probably it. And don't shackle yourself with thinking about paradigms anymore. Perhaps C++ has evolved beyond paradigms. Perhaps indeed we are now paradigm-less, so perhaps you should tell your friends, wives, colleagues, etc. to embrace no paradigm programming. Thank you very much.
Klaus, not so fast. I have a question for you.
One question. Can I read it?
I hope so. I can read it for you, but I don't understand the meaning.
I think so. I read it out loud. How is no paradigm programming different than multi-paradigm programming? Isn't the same S class half full versus class half empty? Well, absolutely true. However, I personally believe, indeed, we are not doing really paradigm programming anymore. And this is kind of the message that I give here. You can think of multi-paradigm programming. Great. This works for me. However, do not start to tell people it's object-oriented or it's functional. It's all of these things. Don't shackle yourself with paradigms anymore. Okay, sufficiently answered? Yeah, okay, I don't know who asked the question. So I hope so. Thank you very much.